So we've focused a lot, I think, on the application of area. And what I want to point out is that it's important to note that the integral from a to b of a function f of x represents area only when f of x is assumed to measure length. And a lot of times we'll have situations, context, where f of x represents something very different. So I want to generalize that idea and consider that suppose a situation where we interpret the interval from a to b as an object of length b minus a. So you can imagine that object being laid down in some sense on the x-axis, starting at a and ending at b. And at every point x within that interval, the function f of x is going to output the density of the object at x. And these can have lots of different interpretations, so this is just a very broad discussion. But what I want to point out here is that kind of more generally, if we think about f of x as being a density function, we can generally think of its units as being a ratio. So the mass units, whatever those may be, divided by the length units. And in this case, if we integrate that density function, f of x, what we get out of that is the mass of the object. So we're talking about mass here. I'm going to say interpretation. For instance, suppose that the density function was measured in kilograms per meter. Then if you were to integrate f of x, what you would get would have units kilograms. One way to interpret that you can think about in general, when you're integrating, you multiply the units of the integrand and the units of the independent variable. X here would be measured in terms of meters. You could also have that f of x gives you the temperature in degrees Celsius per a given meter. And in that case, if you were going to integrate that function, the result would give you the temperature in degrees Celsius. You could also have a situation where f of x measures price per meter. And then in that case, if you were to integrate f of x, then you would get units of just dollars in this case. So these are just kind of more broad interpretations. Like I said, it depends on the context. And for a specific example, suppose we're considering a rod that's 3 meters long. And we're going to let x represent the distance in meters from the left end of the rod. And f of x is going to represent the density of the rod in grams per meter at point x. We want to find the mass of the rod. Well, one thing to think of here is in terms of setting up our interval, we know that we're dealing with a length of 3, but the way that this is described, f of x is measuring the density of the rod, where we're thinking about x is the distance from the left end. Well, that means that when we're at the left end of the rod, x should be 0. So we can think about my interval that we're starting at 0, and of course, because it's 3 meters long, I'm going to go from 0 to 3. So that tells me the bounds. We want to find the mass of the rod, so we want to integrate f of x, and I want to integrate it over the necessary bounds, in this case 0 to 3. So here we can just take this integral. The antiderivative is x plus 5x squared over 2. We're evaluating this from 0 to 3. So we're going to get 3 plus 5 times 9 over 2. And we would get here then 51 over 2. Now, in these contexts, the units are important, right? The density was in grams per meter. And when we integrate this, the result is going to be in grams. So just kind of being able to broaden, it's not always the case that the function f of x we're looking at is just measuring length and therefore we get area. We can interpret when we're trying to visualize, we can make that interpretation, but it's important to be able to extend that to whatever context we may encounter where an integral is going to be necessary to solve a problem.